Hello, everyone. Welcome to the engineering, product, and TPM talks, especially TPM talkers. Welcome to the third part of my take on the X, formerly known as Twitter, system design. In the previous parts, we looked at functional requirements, non-functional requirements, design considerations, and in this part, we want to essentially conclude the design. Okay, stay with me. We'd like to start with a thought of the day. Uh, Today's thought is from Algernon Charles Swinburne, who says, "Fate is a sea without a shore, and the soul is a rock that abides." He says, "Fate is a sea without a shore, and the soul is a rock that abides." Now, let me know in the comment section down below if you can fathom the depth of this thought. I will not even attempt to interpret this beyond saying that we can sail where we want, and it's important to invest in our soul because it is the one constant that we have. Okay. Okay. So in part three, we will complete the application of the system design interview framework to X, formerly known as Twitter. We have already covered introduction to Twitter, goals of the system, APIs, high-level system design, the database schema. And now I just want us to round up data sharding, cache, replications, fault tolerance, load balancing, observability, and monitoring. We've said that it's a tough market right now, and early career opportunities are drying up, which means a lot of people will not have the requisite experience when it comes to large scale, complex system designs. And my hope, hand on heart, is that these series of talks will help you prepare for system interviews, but not just that, will give you ideations, inclinations if you have to design systems um, wherever you work. Okay. So in particular, it's useful for technical program managers when you're having those discussions with engineering or product to query whether the design is suitable for your customers, can fit into the roadmap you've designed, etc. But also for engineers, right, to check that your knowledge, skill, capability matrix is on the right path. Okay, so where are we? We are now at data sharding, right? So we already know that we have a large, huge number of new tweets every day. We said 100 million. Uh, we said our read load is extremely high. We did an average calculation of 650,000, but said it can go up to 1 million depending on whether it's peak time or not. So we need to distribute our data to multiple machines so that way we can read and write, efficiently. Now we have many options to do this, right? How do we shard? One way is we can shard based on the tweet ID, right? So that's the tweet ID. So we can have a hash function that, maps each tweet ID to a random server where we'll store that tweet. Then, if you want to search for those tweets, we have to query all the servers and each server will return a set of tweets. Okay. A centralized server will aggregate these results and then return them to the user. For example, if you consider generating a timeline, yeah, here are these are the kind of steps that your system will take. First, your application, your app will find all the users that person follows. Then the app server will send a query to all the database servers to find tweets from those people. Then each of those database servers will find the tweets for each user, sort them by recency, most recent, and return the top tweets. Then the app server will now merge all those results, package all the results together, and sort them again to return the top results to the user. Okay. So what the sharding based on Tweet ID does is it solves the problem of, if you have hot users, hot, people that are very frequent users, um, but we have to query all the database partitions, which creates load, right? Now, um, we can improve sharding based on Tweet ID by introducing a cache to store hot tweets in front of the database servers. Something else is we can decide to shard based on user ID. Okay. So here in this, we store the data of user on one server, which introduces a risk, but we can pass that user ID to the hash function that will map the user to a database server where we can store all of the user's tweets, favorites, follows, etc. And then when we query for tweets, follows, favorites of that user, we can ask a hash function, right? Where can we find the data of that user? And then we read it from there. The problems with this, remember I said as part of the system design interview, you have to look at different pros and cons. And you have to think about what the risks are. Now, this the shard based on user ID. What are the challenges? If a user becomes hot, say suddenly the user goes viral, then there will be a lot of queries to that specific server, and that server holds all the information. It's not distributed. So while some servers will be hot, other servers will be not as hot. Then over time, some users that are more prolific can, store a lot of tweets, right? Which creates a bottleneck, right? Ideally, you want to maintain a uniform usage pattern, right? You want to maintain a uniform distribution as your user data grows. Yep, that is difficult if you shard based on user ID. Now, my thoughts, let me know what you think, if you think that's correct, if you have a different way around this. I'd be keen to hear other people's views on this. Then you can also shard based on the tweet creation time. So in other words, in this bit, based on you store based on when the tweet was created, right? Now, one advantage of this is that all the top tweets from a particular user can be fetched quickly because they're essentially stored based on timing. We will only have to query, a very small set of servers because it's storing them sequentially. Um, then again, the problem here is that the traffic load will not be distributed. Example, while writing all new tweets, right? All new tweets will be going to one server, and then the remaining servers will be sitting idle, which is not great for capacity utilization. Okay. Then someone could say, what if we combine? Because now we've looked at sharding by tweet ID, by user ID, by creation time. Someone could say, what if we shard based on combining both tweet ID and tweet creation, right? Using two elements to have a fix. Okay. The challenge with this approach is that we'll need, you know, we'll need each of the tweets to be unique, right? We'll need each of the uniques to be unique. So we can go around this. I mean, there are lots of ways we can do, right, to create a unique ID, right? So for instance, we can use the system's epoch time and to do this. So say a tweet ID will have two parts. The first part will be representing the epoch seconds, and the second part will be an auto incrementing sequence. Okay. So to make a new tweet ID, we can take the current epoch time, and then over here we append an auto incrementing, number to it, and then you can figure out, the shard number from this and store it there. We will need 31 bits to store this. Let me just show you what I've pre-done. right? So we'll need 31 bits to store this number. Since on average we're expecting 1100 plus tweets per second, we can allocate 17 bits, not bytes, bits, to store the auto-incremented sequence, the bit that says happening over here, which will make our tweet ID 48 bits long, 17 plus 31. Therefore, that means every second we can store 130,000 new tweets. We can reset our auto-incrementing sequence every second because it's using the epoch time as well. And then for fault tolerance and better performance, we can have, say, perhaps two database servers, okay, to generate the auto-incrementing keys for us. One will be generating the even numbered keys, the other will be generating the odd numbered keys. Now, if we make our tweet ID, say, 64 bits, that's 8 bytes long, it's raised to power 8, 8 times 8, then we can easily store tweets for the next 100 years and also store them for milliseconds at millisecond granularity. Now, in this approach that I've just described, the challenge here will be, we will have to query all the servers for timeline generation, okay, which is a challenge, but we can expect that our reads and our writes will be substantially quicker as a result of this, right? Because we don't have any secondary index on creation time. This will reduce our write latency. And then while in read mode, we don't need to filter on creation time as our primary key has epoch time included in it. So it will be faster to retrieve. A little talk about cache. So we can introduce a cache for the database servers just to cache tweets and users. There are many ways we can do this. For instance, we can introduce an off-the-shelf cache system like Memcache that can store whole tweet objects. We will need application servers, right? Which can check the tweets before they hit the database. Okay? And the reason why is that it can check if the cache has the desired tweets before you hit the database. Saving some system latency. And then based on the client's usage patterns, we can determine, how many cache servers that we will require. Yeah. Then the question can be, what's the best cache replacement policy? Should it be least recently used? Should it be based on the latest data? I think there are different ways to look at this, right? So how do I say? So when a cache is full and we want to replace a tweet with a newer, hotter tweet, right? If we use the least recently used policy, that means that the tweets that have the less views, the least amount of views, will be evicted first, right? If we go with the 80-20 rule where, say 20% of tweets are generating 80% of read traffic, then this will dictate that we only need to cache 20% of the daily read volume. I remember I said the daily read volume could go up to 1 million at peak time. If we look at an alternative cache replacement or eviction policy, say latest data, then, we can say 80% of our users see tweets from the past 3 days. Then if we observe that that's the case, right, that 80% of our users only look at tweets from the last 3 days, then that means we only need to have dedicated cache servers to store users from the past 3 days. Yeah, store tweets from all the users from the past 3 days. 3 days, sorry, 3 days, 3 days. Now, if you're getting 100 million new tweets or 30 gigabytes of new data every day without photos and videos, if we want to store the tweets from the last 3 days, we would need less than 100 gigabytes of memory, right? This data can easily fit into one server, but it's important that we replicate it into multiple servers. as per the system design diagram there, right? Now, in this approach, our cache would be like a hash table where key is the owner ID and then the value will be a double linked list or some other list containing all the tweets from that user in the past 3 days. Now, since we want to retrieve the most recently tweeted data first, the most recent data first, then we can always insert new tweets at the head of the linked list, which means all the older lists will be nearer the tail. And if they are near the tail, it's easy for us to evict those tweets that are, you know, um, older than 3 days to make room for newer tweets. Quite quickly, a word on replication and fault tolerance. So since our system is read heavy, okay, we can have multiple secondary database servers for each database partition. And then those secondary servers will be used for the read traffic only, right? Because we expect to have high read volumes. Then all writes will first go to the primary server, we said 1150 per second, and then they'll be replicated to the second server asynchronously. This scheme will give us fault tolerance. Since whenever the primary server goes down, we can fail over to a secondary server instantly. In terms of load balancing, typically we add load balancers to 3 places in the system. The first is usually between the client and the application servers. The next is between the application servers and the database replication servers. And the third is typically between the aggregation servers and the cache server. Okay. Now, if we use a simple round robin approach at the outset, that will distribute, incoming requests equally among the servers. A load balancer is simple to implement, doesn't introduce any overhead. Another benefit of this approach is that if a server is dead, the load balancer will take it out of the rotation and will stop sending any traffic to it. Now, a problem with round robin load balancers is that it won't take the server's load into consideration, which could be a challenge if you're having hot. If a server is overloaded or slow, the load balancer will not stop sending requests to that server, which could introduce failures. Now, to handle this, a more intelligent solution could be implemented, that periodically queries the backend server to check, hey, how are you doing? How are you doing? How are you doing? And then with that, you can adjust the traffic based on that. Something else that we need to consider is monitoring and observability. Being able to monitor our system is crucial. So you should constantly collect data to get an instant insight into how your system is performing. Okay. What sort of metrics can you collect? Some are on the screen. Maybe you can collect the number of new tweets per day, per second. What is daily peak? We can help us in terms of optimizing the system. We can collect, how many tweets per day how many tweets per day, per second our service is delivering. We can check what's the average latency that's seen by the user, even across different regions. That could help us think about content distribution networks, etc., optimize our system even further. Now, if you monitor these and other counters, then we could realize whether we need more replication, load balancing, or caching. Okay. So there are some extended requirements that we mentioned at the beginning. I'm afraid we may not have time to go into them. How do we serve feeds? Do we want to get all the latest feeds? Do you want to get all the latest tweets from the people someone follows and merge and sort them by time? Or do you want to use pagination so that break them into pages that are defined 10, 20, depending on the size of the pagination? And then we only fetch, the top, say, N tweets from all the people someone follows. Again, pagination typically depends on the viewport of the client. So for a mobile phone, obviously your screen size or your viewport is smaller than if it's a laptop or a MacBook. Alternatively, we can also pre-generate feeds, right? To improve efficiency, we can pre-generate the feed. I will do a video later about, ranking and timeline generation because that is a whole new space. I know I promised a few videos. Just hold me to it. If you don't see the videos in time, subscribe, tweet, subscribe, like, let me know. Hey, you promised this and you've not delivered. That's fine. Um, Trending topics. How do you want to do with trending topics? We can cache the most frequently occurring hashtags, perhaps hashtag free or search queries in the last n seconds and keep updating them after every periodic second. Obviously, if you're doing observability, you'll be able to identify what's the best threshold for this. And then we can give weight to topics which are shown to more people. Um, do we want to recommend who people follow? Do we want to give suggestions? If we want to implement that kind of feature, who to follow will improve engagement. So we can suggest friends of someone who to follow. We can go to 2 or 3 levels down to find famous people for suggestions. We can give preference to people with more followers. As only a few suggestions can be made at a time, right? So only a few suggestions can be made at a time. We can also use machine learning or AI to predict who a user is most likely to follow. Out of scope for this discussion. Then, in terms of external requirements, we also spoke about moments, and for moments, you may want to get top news for different websites or for the past 1 or 2 hours. For instance, the Olympics is on right now. As I'm recording this, the Olympics is on. So people that are following a particular athlete or a particular team, you could prioritize and send that to them. And again, that will just need categorization, supervised learning, clustering. Then you can show these articles as trending topics in moments. Okay, so guess good things have to come to an end. Just to recap, just now we've completed data sharding, we looked at caching, we looked at replication, fault tolerance, observability, and monitoring. Okay, now this is a lot. I admit this is a long one, but I really wanted to get as much as I could in while optimizing for time. If you want these videos to be longer or shorter, just let me know. Comment at the bottom of the screen. Don't forget to like and subscribe. Let me know if you would take a different approach in the comments below. Thank you.